have been told that electric planes are a physical impossibility because batteries are too heavy and dangerous to ever leave the ground. That's a lie. By ditching liquid electrolytes for ceramic solid-state cells, we have finally solved the weight-to-energy puzzle. The era of gravity-bound aviation is officially over. Flight is evolving. Batteries have always been too heavy and too dangerous for the sky, effectively grounding the dream of electric flight for decades. But by stripping away volatile liquid electrolytes and replacing them with ultra-dense ceramic cells, we have finally broken the gravity barrier. This is how solid-state technology is doubling energy capacity today. Traditional liquid lithium-ion batteries have hit a ceiling of around 300 to 350 Wh per kg energy density because of fundamental material limits in their graphite anodes and intercalation type cathodes, making them too heavy for long-range flight compared to jet fuel's 12,000 Wh per kilogram. Even with incremental improvements, the chemistry cannot deliver the leap needed for commercial aviation. High energy density increases risk of thermal runaway, and aviation requires extreme reliability across wide temperature ranges, which current liquid electrolytes struggle to provide. Adding more batteries increases stored energy, but each battery adds significant dead weight. Batteries weigh around 40 to 50 times more than fuel. Aircraft engines must generate extra lift and thrust to carry that weight, which in turn consumes more energy. The result is a diminishing return. The transition from traditional liquid lithium-ion batteries to solid-state designs represents a fundamental shift in both safety and performance. Traditional liquid electrolytes contains organic solvents like ethylene carbonate mixed with lithium salts. It is highly combustible. A single puncture, short circuit, or thermal runaway could ignite mid-flight, which regulators deemed unacceptable for passenger safety. It requires cooling system and heavy casings that adds weight. It requires bulky packaging and separators to contain liquid safely. It has a limited voltage window. It decomposes at higher energy densities. While solid-state electrolytes are ceramic or polymer based, which is non-flammable, it's ultra-light rigid separators that block dendrite growth, preventing internal short circuits. It provides higher energy density without proportional mass increase. Aviation can rely on safer operation under extreme conditions of temperature and pressure. By neutralizing fire risks with solid-state chemistry, we are moving beyond experimental prototypes into scalable regional travel. Solid-state designs pass the tests from global aviation authorities, demonstrating that even under extreme stress, overcharge, puncture, high-altitude pressure changes, the cells do not ignite. In 2026, the rollout of 19-seat and 50-seat electric commuter planes marks the first wave of certified short-haul regional services, with United Airlines, Misa Airlines, and European startups like Aro Aero leading deployments. These aircraft are now servicing regional hubs on routes under 250 miles, offering zero-emission flights and reshaping commuter aviation. Electric aviation cuts carbon emission to zero. Electric motors cut noise by 75%, enabling flights into smaller regional airports. It improves operational economy by lower maintenance costs due to fewer moving parts, but constrained by battery range. As electric commuter planes takes to the skies, they face three critical challenges that define their future. First, range limitations. With a ceiling of just 250 to 300 miles, these aircraft are restricted to short-haul routes, perfect for regional hops but far from replacing long-distance turboprops and jets. Second, infrastructure. Regional airports must adapt. Charging stations, battery swap facilities, and grid upgrades are essential before electric fleets can scale. Third, scaling more seats. Moving from 19-seat prototypes to 50-seat commuter planes magnifies the weight-to-power ratio problem. We are witnessing the end of the gravity-bound limitations that have historically crippled battery-powered aviation. Next-generation solid-state batteries are finally delivering the energy density required to lift commercial loads without the dead weight of traditional liquids. Flight is being reimagined as we speak, powered by the most stable energy transition in history.